Okay, let's get started. Welcome. Hi, everyone. Welcome to the C3 AI DTI seminar series for the fall semester. My name is Richard Zhang, and I am an assistant professor at the University of Illinois. I am co-organizing and co-hosting the semester's seminar series with Gary Joshi, who is an associate professor at Carnegie Mellon University. Before we begin, we would like to pause to acknowledge the support from our academic and industry partners, for which we're deeply grateful. So the fall 2022 series is organized around two special themes: adversarial machine learning and distributed and federated learning. Our talks are scheduled to alternate between these two themes over alternating weeks. And we have some really exciting speakers lined up for the semester. Just to give you an idea, for the next few weeks, we'll be hearing from Eric Xing, also from Carnegie Mellon University, Tom Goldstein from the University of Maryland, and Rachel Cummings from Columbia University. And our series will extend all the way out to December. Some of the speakers featured here, and you can find more detail on our website. So you can find the abstracts and future talks, videos of previous talks, both from the current seminar series as well as in the past series, will be available on the YouTube channel. And we invite you to subscribe to our newsletters and our channels so that you don't miss these talks. Today, we're very delighted to welcome Professor Zico Kolter to share his research with his talk entitled New Approaches to Detecting and Adapting to Domain Shifts in Machine Learning. Zico Kolter is an associate professor in the computer science department at Carnegie Mellon University, and also serves as chief scientist of AI research for the Bosch Center for Artificial Intelligence. His work spans the intersection of machine learning and optimization, with a focus on developing more robust and rigorous methods in deep learning. In addition, Kolter has worked in a number of application areas highlighted by work on sustainability and smart energy systems. He is a recipient of the DARPA Young Faculty Award, a Sloan Fellowship, and Best Paper Awards at NeurIPS, ICML, Honorable Mention, AI Stats, Test of Time, IJCAI, KDD, and PSG. So with that, I'd like to welcome Professor Zico Kolter. So the talk will be 15 minutes. So for the audience, please go ahead and use the Q&A feature in the Zoom seminar to submit your questions, and we will ask these questions at the end of the talk on your behalf. Thank you very much. So whenever you're ready, Professor Kolter.
All right, so I'll share my screen now?
Yes.
All right. Okay. Hi, everyone. It's great to be here. And I'm excited today to talk about some of the work we've been doing on detecting and adapting to domain shifts in machine learning. This really, I should highlight, is work by my current former students. So Vaishnav Nagarajan, Christina Beck, Yiding Zhang, Sachin, Minji, and Aditi, our colleague Aditi now, Raghunathan, also faculty here at CMU. And they were the ones that were sort of doing the majority of this work, but and links to all the papers are in the are in the slides. All right, so what is the problem that we're trying to sort of deal with at a high level here? The problem that this talk deals with is the setting of distribution shift or domain shift in machine learning. And I want to start by just talking about what is that and why does it matter so much? So the setting that we all know about machine learning is that you draw some training set from some distribution, you draw your test set from that same distribution, you train your training set, and then because you have a holdout test set, you can always get a good estimate of your system's performance on the true underlying distribution by the test set, right? By sort of the basic principles of statistics here. And so this is sort of the underlying principle, I would say, of basically all machine learning, why we claim that machine learning works. But the reality, of course, is that when you actually want to deploy machine learning, oftentimes you are not faced with the same distribution you used to train things on, but you are faced with some other distribution coming from the world, right? And you train on scenes of a car driving in one environment and need to test the same system on a car driving in a different environment or in rain or snow or some other effects, right? And the question that sort of motivates the majority of this talk here is, how do we understand our performance and improve our performance in this setting? And the key point that I want to highlight here, and why I think this is such a crucial problem in all of machine learning, is that this is not an edge case. Okay, this is not some unusual circumstance that we might encounter sometimes. This is every single machine learning system you will ever deploy in the world. Things are never as they were when you train. And every time you deploy a machine learning system, you will encounter scenarios and just different types of data that you did not see at training time. This is the real world. And in this sense, I know that the sort of the theme of this colloquium is on adversarial machine learning, which sort of involves actual, which is a form of this that involves actual adversaries trying to manipulate that distribution at sort of deployment time. But I think in a lot of ways, this setting of distribution shift, including kind of incidental distribution shift, is even more general and even more important, because adversaries may be there. And I think adversarial machine learning is a hugely important topic. And the security of AI models, generally speaking, is crucially important. But from a standpoint of deployed machine learning, this problem of distribution shift, I am convinced, is the crucial question to understanding how well these methods will actually work in practice. So before I start jumping into kind of some of the work we've been doing in our in this setting, I want to lay out as an outline what some of the core problems are in this basic setting. And the really core problem is, how can we perform well on the distribution of data given by the world without having to go to the effort of retraining our system from scratch every time the world changes in some way, right? Because collecting a whole new labeled data set and retraining on that data set and doing all this every time we see some shift in the real world is just not practical. And moreover, it's not what really happens, right? We train our data on, we train our machine learning models on some held out data, when we deploy them in the real world, and they are off on their own. And we need to understand how they're going to perform, and we need to understand how we can make that performance as good as possible. So how can we do this? How can we perform well without access to sort of new labeled data when we're on some different distribution? So the first thing I want to emphasize is that this problem is impossible. It's a good way to start out any talk, I know. But if you don't constrain the set of sort of, in some sense, allowable distributions or allowable changes, then of course this is impossible, right? It could be that your task in the world somehow, the definition of labels flips from what it was at training time, right? Up is down and down is up and things like this, right? That could always happen in this generic formulation. And if you don't somehow constrain yourself, then this problem is going to be impossible. Now, what this has led to is a lot of sort of, I would say, kind of theoretically justified work that talks about limiting the amount of shift that can happen between train and test. Right? And that is a very sort of valid notion of approaching this problem. However, I'm actually not that concerned with these things, because if you start talking from the beginning about KL divergences and the distance between distributions, you're already away from sort of anything remotely practical to really matter to me. And so what I'm more interested in is, in practice, for data that we actually see between training time and test time, how well can we, or I should say training time and sort of deployment time, how well can we actually do? And if things change, can we improve in practice at all? Or maybe even first, before I get into improving performance, can we even predict how well our machine learning models are going to work? right? Can we even get some notion, without relabeling data, without getting a new labeled data set, can we even get some notion of how well the models will perform without explicit labels on our new data? And so the first portion of this talk is actually going to be about this issue here, about ways we can start to do this. Okay, this is based upon 2 papers by my students and former students, Yading, Vaishnav, and Christina, as well as a collaboration with Aditi Raghunathan, also a faculty member here at CMU. All right, so before I start with this, I want to also state something up front, which is that this problem of just evaluating classifier performance without labels is, of course, also impossible, right? If you don't have labels, you could still be in a scenario where things look exactly the same as they did at training time, but your labels have flipped. So you have, 0% accuracy or some very small percent accuracy, right? But again, that's not what we typically see in practice. And so the question I'm concerned about is, in practice, how might we go about getting a sense of how we're going to perform on these new changing distributions? So let me start off by telling you about a very peculiar phenomenon that we found to be true in a lot of these scenarios here. So one thing we found is that if you don't have labels, right, there isn't a lot you can do. If you have a single classifier predicting stuff on your data that's coming in from your machine learning deployed system, there isn't that much you can do. However, if you train 2 classifiers or a collection of classifiers, now all of a sudden there are interesting phenomena that appear to emerge. Okay? And so I want to describe a very peculiar but sort of really, I think, sort of fascinating experiment that we did, now going back a couple of years, which is the following. Suppose you take some data set. I'm actually not even talking about distribution shift here. I'm just talking about a single data set, on my trained data and test data. Suppose I take my data and I train 2 different models on the same data set, the same training set, using, and these are, normally 2 models would be the same, but here these 2 models are going to differ because you initialize them differently, or you just feed the data in a different order to these different models, something like that. And I'm going to compute, not just, I can compute their accuracy because on the small data, I actually have labels, but I'm also going to look at how often these 2 models disagree with each other. How often do they make different predictions? Okay, and obviously, computing disagreement between two classifiers doesn't require any labeled data, right? You could do that in other settings. So this is sort of a potential approach here to start getting at problems with unlabeled data. But if we do this, we find what I think we did this rather, and we found what I think is really sort of a shocking thing. What we find is that the disagreement between 2 classifiers trained in the exact same manner on the same data set, just with different initializations for their weights. These are deep neural networks in this case. We find that the amount of time that these 2 classifiers disagree with each other, so that fraction of the time, the proportion of examples for which they disagree, that is a very close approximation to the error that classifier has on the test set. Now, I want to sort of pause and just emphasize that, because that doesn't sound like that kind of an amazing thing, but it really is amazing. I would think, so these plots on the right here, what they show a data set called CFAR 100. And they show on the x-axis the disagreement between 2 pairs of classifiers. So each dot here actually is 2 classifiers, a pair of different classifiers, where the percentage of the time they disagree is on the x-axis, and the average test error of those 2 classifiers is on the y-axis. And what we find is that there's this amazing correlation between these 2 quantities. And this to me is fascinating, because you would think that 2 classifiers trained on the exact same data even if they didn't perform that well, right? Even if they got 40% error or whatever, right? They would still tend to make the same predictions, right? They're training the same data after all, the same classifier, just training different initializations, right? It turns out though that this is not the case. These two classifiers disagree a lot, and that disagreement is very close to their error. Furthermore, this property doesn't just hold on sort of the in-distribution data, but it also works sometimes, kind of, on when also evaluating how well these classifiers work on out-of-distribution data. So OOD stands for out-of-distribution. And what we have here on the right now is another data set where I'm also going to be plotting the disagreement between two classifiers on the x-axis, and on the y-axis, the average test error of those two classifiers. And this is now on a data set called PACS. It basically has a bunch of images where the images are either photos. PACS stands for photos, arts, cartoons, and sketches. So these are either the same types of things like cats and dogs or other sort of simple classes, but certain data sets are artistic drawings, some are cartoons. So very, very different notions of sort of what kind of images you might actually see. And by the way, it's going into a point I had before, there's no way to describe, the distributional distance between images that are cartoons and images that are photos, right? This is something that we can't really do with these notions, or can't easily do without very, very powerful notions of distributional distance. And most techniques we have, they just don't really work. So what's fascinating is that even on data like this, you still, if you train, for example, on art, so this title of this plot here means that we're training these classifiers. Oh, sorry, we're evaluating here on art, and the sort of the type of data here that we're showing there shows what we trained them on. So obviously, if we train them on art, they do quite well. But if we train them on other sources like photos or cartoons or sketches, they don't do as well. But still, we're able to provide an estimate for how well the classifiers work just by evaluating the disagreement between two classifiers essentially trained basically with different random seeds. Okay? And that is just this amazingly powerful tool that we have here, at least to potentially get started at talking about how well can we start quantifying the performance of our classifiers on unlabeled new data that's very different from what it's seen before. Okay, now there is some theory about why this might work, which I actually don't want to get into here. It has to do with calibration of classifiers, and I think it's actually not, it's very interesting, but it still sort of pushes the question back a little ways. The point I actually want to make here is that this is a very interesting phenomenon, but it's not quite reliable enough yet to really be something you would sort of bet you would bet too much on. Because if you look at the figure on the right here, I want to sort of take you into these blue squares over here, right? So those blue squares are actually the point where we're kind of actually violating this similarity between disagreement and test error. So these points here are all pairs of classifiers, and they have disagreement in the 20% or so. So that would suggest by this simple logic that maybe their error is going to be about 20% too, but it's more like 60% here, right? So you wouldn't really want to trust this. There's no sort of built-in notion in this model. And I should emphasize, if you don't actually have labeled data, you can't actually compute the y-axis here, right? This is sort of just for evaluation. All you could compute would be the x-axis. So all I can compute is that these disagree with each other 20% of the time. You might estimate that that means they're going to have 20% error, but in this case, you would be wrong. So actually, what I'm going to spend the majority of this time, this portion talking about, is a slightly more involved approach for evaluating this same thing. But I'm highlighting this first here because this notion of disagreement is a very powerful one, and we're going to leverage this just in a different way in the next section. Okay, so this is the starting point, and now I'm going to introduce another set of techniques that wind up giving us what ends up being a much better estimate of out-of-distribution error for a classifier without any labeled data using this same idea as disagreement. But so to get started, I actually want to bring up another piece of work done by some other students and faculty at Stanford and beyond. And they identified something known as that we call a phenomenon that we call accuracy on the line. So I need to emphasize this is a different, these are now different axes of plots here. What they are now showing, and this axis must have gotten cut off here, so apologies for that. What they are showing here is they are showing a plot of accuracy of many different classifiers, where the x-axis here shows the accuracy on the in-distribution test set, and the y-axis shows the accuracy on some out-of-distribution test set, right? So you evaluate, in this case, this is a CFAR classifier. The CFAR 10 is a very common data set we use to evaluate machine learning classifiers, kind of a toy problem. In this case, we've built live classifiers. They perform to varying degrees of accuracy. And you evaluate it on some modified version of the data set. Actually, this is a modified data set called CFAR 10.2, which is very similar, but has some kind of hard to describe types of shift involved. And what we see is that on the y-axis, what this means here is that the performance has a noticeable drop between the in-distribution performance and the out-of-distribution performance, right? So if the out-of-distribution performance was exactly the same as in-distribution, all their points would be exactly on this dotted line. But what we see, and this is the core problem of out-of-distribution data, is that there's a notable drop here. Okay, but what's important here is actually not that there is a drop. What's important is that there's an amazing linear correlation between in-distribution accuracy and out-of-distribution accuracy. And this is a phenomenon that they've called accuracy on the line. And this doesn't seem maybe that surprising at first, but it's actually an equally surprising phenomenon as many that I'm going to show you today. Because what it means is that even though classifiers, better and better classifiers, deep learning classifiers usually are the best ones these days, right? That we train on data sets like ImageNet, like CFAR, these sort of classical benchmark data sets. What these sort of plots say is that when you take these classifiers and evaluate them on new distributions of data, their performance will drop. But there still is a very strong correlation between the best classifiers on the ImageNet test set and the best classifiers on some new distribution, which is actually very good for deep learning as a field, right? Because it means that all the work we've done to improve performance on these, assortment of a few collection of benchmarks actually seems to translate to some better performance on other data sets too. So this is, in some sense, these plots kind of justified all of machine learning in the last 10 years. I'm a bit tongue-in-cheek when I say that, but this is sort of a very interesting and honestly kind of a relief to some extent. But the point I want to make now is that this is a really nice thing to have, but it's not actually very useful when it comes to estimating the performance of a classifier out of distribution. Because to create this plot, you need to be able to evaluate accuracy both in distribution and out of distribution, which you can't do unless you have labeled data out of distribution. So if you just get new data from the world with no labels, you really can't do this, okay? So despite the fact that there's this sort of nice linear approximation here, or linear relationship between in distribution accuracy and out of distribution accuracy, and what I mean by that is, there's some slope and intercept term to this line, basically. We can't really do very much, practically speaking, with this. Okay, so what my students and what we sort of continuing this line of work, but with this notion of agreement kind of in our minds from our past work here, we looked into this more and found another, the third, I guess, in this section, very interesting and surprising phenomenon here. And so what we found is that this linear relationship between in-distribution performance and out-of-distribution performance, this holds not just for accuracy, but it also holds between the pairwise agreements between large sets of classifiers trained on these data sets, right? So if I take a whole bunch of classifiers, look at their pairwise agreements in distribution on the test set, and their pairwise disagreements on some new data set, which I can do both of those, by the way, without any labels whatsoever. Those points also lie on a line. Okay. And what's very surprising, or sometimes, they don't always, but they very often lie on a line. And you actually can check this property of lying on the line without any labeled data, right? Because you have access to all of this without actually ever seeing, any labels for either the in distribution or out of distribution test sets. What you find is that these agreements also lie on a line here, right? And this is surprising, but what's very interesting here is that this line seems to be approximately the same line as you see for accuracy. So what I'm plotting here are the purple points in, or the pink points, which are the plots of pairwise agreements, and the blue points, which are plots of corresponding accuracy. And we see that these basically make up the same line. Not always, so sometimes like neither really lie on the line here. And actually in this case, the fact that the slopes are the same is somewhat incidental. But when they're both on a line, that line looks approximately the same between accuracy and agreement. And now all of a sudden, this leads us to an extremely practical approach to estimate the accuracy of a set of trained classifiers on some new data set or some new distribution without any labels on that new data set. And so the idea is actually very simple here. The idea is we're just going, basically we have 3 knowns and 1 unknown. So we know through just unlabeled data, we can get the agreement of classifiers out of distribution and the agreement in distribution. We can use that data to estimate the slope and intercept, this A and B terms, for the agreement on the line phenomena, if it exists, or we can also verify that it doesn't exist, that this seems to be sort of not actually happening here. So that lets us, using only unlabeled data, we can evaluate or estimate what the slope and intercept is. And then once we have that slope and intercept, we can get an estimate of an algorithm or a machine learning model's out of distribution accuracy by just taking its in distribution accuracy and plugging it in to that exact same equation. Okay? And so by only access to labeled data from the in distribution settings, this is our normal kind of test set we use to train our algorithm, and unlabeled data from our new sort of from the world itself, we can form a reliable estimate of how well a classifier will actually work in the world. And this method typically outperforms a wide variety of competing approaches and winds up being really one of the best ways we have of doing this estimation. Okay, so that's sort of part 1. That was about estimating performance, okay, without labeled data. But what if your performance is just bad? and the answer to a certain extent is your performance is not going to be good on this new data set. What do you actually do? Well, you could certainly retrain your whole classifier, collect more labeled data, retrain it. And in the worst case, you will have to do that, right? So in the worst case, you will indeed have to do this. But there's another question I have here, which is that can we maybe do better than this? Can we maybe leverage some of that unlabeled data to just directly improve the performance of our classifier without resorting, at least initially, to just collecting a new labeled data set and retraining from scratch? And the answer seems to be yes, we can, at least in some cases. And so to motivate this, I also want to go to some other work. This is actually, again, not by us. This is some work out of Berkeley and Adobe Research and others, or at the time, Adobe Research and others. And I want to introduce the algorithm called the 10th algorithm. The 10th algorithm approaches this exact same problem. It sort of says, and this is actually relatively recent. It was from last year at the iClear conference. But what it does is tent is a way of adapting trained classifiers to some new distribution or some new sort of set of examples without using any ground truth labels on that new data. And the way this works is you take just your unlabeled data, you form the predictions. So here HI is like the probability that your model, the probability of class I that the model predicts to assign to class I, right? The probability that the model predicts class I. And you minimize this quantity called the entropy of these probabilities. Okay, the entropy of, in fact, to be even more specific, the entropy of the model's what are called the softmax outputs of the model. And that's basically doesn't require any labels because you just take your unlabeled data, you feed it into the model, and you minimize this entropy function. There's a bunch of other details to this algorithm, but that's the basic idea of this algorithm. And this algorithm works, and it works surprisingly well. But I need to just emphasize just how bizarre it is. And so what I'm showing here on the left are, for various domain shift problems, settings where you're evaluated on a different domain than you were trained on. There's this classic sort of benchmark for this called CFAR 10C for corruptions and CFAR 10 or 100C, and the same for ImageNet, et cetera. And what we find is that if we take a model and train it on, say, CFAR 10 and evaluate on CFAR 10C, it gets like 30% error. And that's down from, 4% error for the original classifier. But then if we run tents, so we just run this algorithm where you minimize the entropy of the predictions, we bring that back, not all the way, so we're not sort of at the best performance possible, but we bring it back to like 13% error. Okay, a little bit worse for other classifiers too, but still we substantially improve upon the performance of the classifier. And I need to emphasize just how weird it is that this works. What tent is doing is it is just basically making the predictions more confident, right? That's what entropy measures, sort of how confident you are in your predictions. And not in a single example, but when you optimize over a whole batch of examples, making those predictions collectively more confident with the right tuning and the right regularization and stuff like that drastically improves the performance of the actual methods. And again, I can't stress just how weird it is that this works, right? Like, why on earth would you want to just make predictions more confident, right? Like, and even if you did, I mean, why would this softmax entropy objective be the right one? I mean, it sort of, it's one measure of sort of confidence, but like, why would you want to minimize that? I mean, what's the possible rationale for doing so? So we found this sort of very, very strange. We sort of say, okay, this seems to work. There seems to be something to be said about optimizing some function of the new unlabeled data that you see sort of in the real world when you see distributional shift. I mean, I shouldn't say real world, but under some changing conditions. These are synthetic examples, I know, but under some changing conditions, you might want to do something to sort of optimize your classifier. But it couldn't possibly be the case that like this random choice of softmax entropy is the right thing to do. And so we had an idea. And our idea was to employ a technique called meta learning. I don't want to go into the details here. There's going to be actually a little bit more math, but the math in this slide and others, but the math isn't the important part. I'll try to give the high level idea through all of this. I'll have a little bit of math because I do in fact work with math, so it's fun to include some. But our thought was there seems to be some value in performing this sort of minimization of our predictions, of some function of our predictions, right? So our classifier basically is, this function h. there seems to be some value in minimizing some function, I'll call here L, big L, applied to our classifier's predictions. But I don't know what that function should look like, right? I mean, that's just some, kind of theory. We know that entropy kind of works okay there, but there has to be better functions out there in the space of all functions. And so what we did is we used this procedure called meta-learning to essentially learn what would be the right objective to minimize, such that when we encountered a new distribution, minimizing this mysterious function L would improve performance the most, okay? And so we ran this approach. The details are not too important here, but basically it provides us a way of learning functions L that are well tuned to this sort of idea of minimizing them at test time to improve performance. And we find that we are in fact able to marginally, but very reliably improve over what Tent was able to do. Okay, so here on the right, the original performance is here, Tent is there, and our meta-learning approach gives modest but still statistically significant improvements over a large range of domains. I'm showing one here, but this is pretty consistent over a pretty wide variety of domains. So it works. We're going to write up a notice paper, and everyone will be happy. Before we did that, though, we wanted to sort of check one last thing, which is what is that function we're learning? Right? We can plot it. We can plot what these things look like. What is that function, that L function we learned? What does it actually look like? And here it is. Here's the function we learned. I'm showing it in blue there. The meta-learned function. Also showing softmax entropy there, which has a higher error when you use that to adapt your classifier, has higher error than our meta-learned loss. So black is softmax entropy. Blue is our meta-learned loss. And the bizarre thing here is that here is a fitted version of entropy where we just have one additional parameter that we scale. Basically, it's called temperature scaling. It sort of involves just one additional parameter to softmax entropy. And that is an amazingly good fit to this function we learned. In other words, we allowed our meta loss to be basically any function. So we could learn the single best function possible for adapting classifiers to test time performance, right? And what we found is the best thing to do seems to be minimize, a scaled version of entropy. That seems why, and in fact, it actually even does better. So if we use the sort of scaled entropy, it actually gets even a little bit lower error than our meta loss. So what on earth is happening here? Somehow this function that seemed completely arbitrary of minimizing softmax entropy wound up being exactly what we learned if we allow ourselves to learn any function. So this paper we all thought was just doing this hacky arbitrary thing actually seemed to be doing the exact right thing. It turns out this is amazingly consistent. So you tried different classifiers, different data sets, different training methods, different learning rates, everything. This was super, super consistent. The one thing that would change this effect here, that would make this meta-learned function no longer the softmax, basically the entropy function, is if you trained your classifier with a different loss function. So here we're actually training our classifier. Normally you train classifiers with a loss function called cross entropy loss. Here we trained it with a different loss function, namely squared loss, so like a least squares kind of error. And that now makes our meta loss that we learn look like actually a negative quadratic function. But that's like the only thing we could do to actually make this thing change notably. So this really had us stumped. What is going on here? Why was this happening? Why was, of all the functions we could learn, this Tent algorithm the best, except when you train using squared error? And so what is happening here? And now I'm actually going to dive a little bit, for those that have been kind of following along here and want a little bit more math, a little bit more deep dive. I'm going to satisfy you guys now, or guys and gals now. To be clear, we don't know what's happening. Okay, but we have noticed something kind of interesting, and to explain it, we're going to need to use a bit of math, and particularly talk about the concept of what's called a convex conjugate. All right, so now I'm going to do a little dive into a bit of detail about what we think might be happening here. And don't worry, so the next, I would say, 5 slides are going to be a little bit of a deep dive into it. But for those that are sort of, this gets a bit too detailed, don't worry, we'll sort of pop out in the end and talk about the implications of this approach. All right, so what is happening here? Well, I'm going to introduce this function called a convex conjugate. A convex conjugate is like one of these foundational techniques in convex analysis, the analysis of certain classes of functions for optimization. And what it basically is the convex conjugate of if you have some function f that is a scalar valued function, the convex conjugate is defined as the supremum over x. The convex conjugate of y is defined as the supremum over x of a linear function, x, the inner product of x and y, minus f of x. And the details here aren't really important, but just what you can know is that the convex conjugate is a sort of a foundationally related function to sort of for convex functions f, and it's related to things like convex duality and things like that. So without getting into too much detail, it's an important transformation of functions that sort of provides a lot of useful insight into the optimization properties of functions, and it's just defined this way. Okay, and it turns out also, when f is differentiable, you can even define it a little bit. The optimality conditions, therefore, this function sort of deal very naturally with the gradient of f and things like that. Okay, so that's sort of where we start. Now, how does this relate to training classifiers? Okay, so this seems like I'm taking a really bizarre detour, right? But it turns out that the loss functions we use to actually train deep networks are all expressible in a way that essentially mirrors the problem, the optimization problem associated with the convex conjugate. What I mean by that is, in a bit more detail, is that typically the loss functions we use in machine learning are some measure between the sort of difference between our hypothesis class H and our true labels Y, right? This is sort of the foundation to a lot of machine learning. And the loss function used by most machine learning actually has is of the following form. There's some function applied to our hypothesis class minus a linear term between our labels, considered like, a one-hot encoding of our labels or things like that, and our hypothesis, okay? And so that's actually all I'm going to say here. I don't want to get into too much detail here. Things like the cross entropy loss or the squared loss actually can both be framed in this manner. Okay, so that's the core idea here. All right, and what's interesting now is that if you look at the actual optimization problem associated with minimizing the loss of a classifier, you sort of find this interesting relationship here, which is that if you think of, what a classifier is really doing is that it's minimizing the sum of losses, right? The sum of these losses. But if your classifier is sort of rich enough, which it typically is for deep networks, this is actually kind of like minimizing each example arbitrarily over the output of the hypothesis class. And this optimization problem here is exactly what the convex conjugate actually is defined as. So this is actually just equals the convex conjugate. And plugging in the last step, the optimality conditions for the conjugate, you actually get a formulation like this, which is the convex conjugate applied to the gradient of our hypothesis class. Okay, so that was sort of a long chain of thought there. It's also not actually a formal proof at all. It's just sort of a very informal argument. But it says something very interesting. So without getting into too many details here, what I will say is this form that I have on the right, which is some sort of function of the convex conjugate of our something like our loss function. This function on the right does not involve the actual labels of our data set at all, right? So by a series of transformations, we've actually removed all sort of use of the labels in transforming this loss, okay? And the only real point I want to make, don't worry at all if you sort of, that went by too quickly here. The only point I actually want to make is that this transformation, this sort of reliance on the convex conjugate, this exactly captures the effects that we saw empirically in our test time adaptation. In other words, for cross entropy loss, which is the loss people actually use to train deep networks, the corresponding kind of unsupervised version of that loss is softmax entropy. That's what Tent was optimizing. If we use squared loss, the conjugate function we recover is negative squared error. It's the exact thing that we saw in our two examples of meta learning there. And this is really sort of a fascinating connection that we don't fully understand, to be very clear. But I think it is a really foundational insight into what's happening with sort of test time adaptation. That somehow, when we apply this mechanism of convex conjugacy, we're able to recover what seems like the optimal kind of empirical thing to do for test time adaptation. One last thing I'll say is you can also interpret this not just as sort of convex, a convex conjugate, you can also interpret it as a kind of pretend label that we're making up. So it turns out that you can also interpret Tents and other algorithms as kind of creating pretend labels from the existing classifier and then minimizing your loss as if those were the true labels. This is a technique called pseudolabels, and you can also interpret all of this as a specific way of finding pseudolabels as dictated by the conjugate function. And so, in fact, one way to interpret this thing is basically that our convex conjugate gives very natural pseudolabels to use for test time adaptation. And this is actually also how you want to implement it in practice. So the real benefits, though, so it's like I've gone through a lot of math here, and so far there hasn't really been very much payoff, right? Because all I've done is sort of recover that the thing we were already doing, which was this 10th algorithm, was kind of the right thing to do in some respect. And so the real benefit of this, of course, is not just that it kind of recovers 10th, though I think it does. I mean, in some ways, I think actually sort of describing what 10th does and providing a justification for 10th is in some sense one of the most important contributions of this work. But I would also argue that what's really important about this is this also gives us a way to create test time ways of adapting classifiers to unlabeled data for classifiers trained using other loss functions. So this is a recent trend in machine learning as people have developed kind of new, better loss functions that perform better in some scenarios. So in fact, actually just as we were doing this work, we looked at ICLR, the most recent conference, for a bunch of potential loss functions, found one called polyloss. And it turns out polyloss you can also write in a sort of not quite the same form, but a very similar form to what we had before. And it turns out using the same formulation, you can derive kind of what's the right conjugate or what are the right pseudolabels to use for this polyloss. And what we find kind of very consistently is that when you apply this methodology to pseudolabels, you get performance that outperforms tent or other possible sort of objectives than rather our method using these specific type, what we call conjugate pseudolabels, works better for test time adaptation than all other approaches we can find. So if you compare it to just tent, if you compare it to sort of using the right loss but the wrong kind of pseudo label, we find that we consistently, I mean, maybe modestly in some cases, but consistently outperform previous approaches. And this also works, these are sort of synthetic examples that I'm showing here, but this also works on other domain shift benchmarks. Like, for example, training a classifier on one type of digit recognition, Street View housing numbers is a classic data set, but then using it to classify USPS or MNIST digits, we find that, again, if we use our original classifier that's not adapted, we do quite poorly when we transfer to a new domain. If we use tent, we improve a lot, but using our method in yellow, we get better performance and better domain adaptation to all these things. Okay, so that's actually the summary of what I want to talk about mainly. I'll just end with a few final thoughts here. As I said, this problem is impossible in practice. But yet, despite in theory, there being no way to actually solve this problem, it does seem like we are able in many cases to practically improve upon the performance of either estimate performance of classifiers or improve upon the performance of classifiers. And so I want to just end with a few thoughts about the bigger context of distribution shift. So the problem of distribution shift is fundamentally ill-defined. Okay, if I tell you the data you have in the world differs from the data you have at training time, I can always create a setting where your classifier that you've trained on your training set will perform arbitrarily badly in the real world, right? And you have only unlabeled data from the real world. I can always create a scenario where you will fail if you try to do this. So the bigger question I have here is how can we quantify what methods will actually work for what types of distribution shift? And there's sort of two approaches that people take to this. The first approach is what I would call the first principles approach, which is kind of saying, let's maybe talk about trying to characterize using some notion of distributional divergence. Let's try to characterize the types of shift that actually where we can work on, where these things can work. And the whole fields like distributionally robust optimization, like many other areas, these actually all kind of fit into that framework of trying to characterize first sort of theoretically what types of shifts are allowed and then going from there. But to me, this is actually unsatisfying because it's very hard to create sort of notions of divergences between distributions that can capture, going from photos of cats and dogs to sketches of cats and dogs, or we should capture a scene from a car in the summertime to one in wintertime. There's no real overlap between those two settings, except in in some underlying representation that we may or may not be able to learn. So what I'll leave with here is just this notion that I think we can take, in some sense, these approaches but flip them on their head. In this talk, I've talked about two different phenomena that we've observed empirically, which allow us, in some cases, to evaluate machine learning algorithms without labeled data, agreement on the line and similar effects, and sometimes improve their performance, namely things like test time adaptation with tent or these conjugate pseudolabels actually working. And I actually think that these effects are in some sense a better characterization of drift. So rather than looking for drift that is within a KL divergence of epsilon between two distributions, let's think about the set of drifts that obey accuracy on the line or for which tent works, and try to better understand those types of drift, those types of distributional shift, and understand how these things are all related to each other so that we can know and have some confidence in how our machine learning methods will perform, even though they are deployed into the real world where things are changing all the time. So thank you very much. Happy to take some questions now, but if you're interested, these papers and others, actually not quite yet because they're still under review, but these papers and others will either be out or shortly out on my website, and happy to take any questions you may now have. Thanks very much.
Thank you very much, Zico. So our Q&A function is down below here. And
okay, great.
So while we're waiting for people to type their questions, and I'll squeeze in a quick question. So you mentioned that, so you kind of view adversarial examples as sort of a special case, right, of distributional shift. I'm just wondering, like, now if we were to bring some of these results back to adversarial machine learning, what would be some of the takeaway, do you think?
So, right. I think actually this is actually quite difficult to honestly take things back from these methods to adversarial learning. And the reason why is that these effects, they're all empirical phenomena, right? There's no reason these things have to work. And adversarially, you could always make them not work. Okay, so there is no way, in some sense, to actually know when these will work and when they won't work, except to say that for real shifts we observe in practice, they seem to work. They seem to work okay. All right, and that to me is quite important, is the way I would sort of phrase it, right? Because despite having worked in the area for a long time, and and we work in the area, and so I have every incentive to try to hype up the importance of adversarial robustness. I'm actually quite skeptical, or getting more skeptical of its importance relative to these other settings of drift that we have. And the reason is very simple. It's that we don't see it. We don't see these things happening that often. Right? So if you look at the actual challenges that machine learning methods face, they don't face problems because they're under attack, right? They face problems because there is never a setting where our actual deployed performance equals test performance, right? Things always look great in the test set.
That's right.
You spend a long time evaluating them, and it works great. So adversarially, these methods can all be broken, just like normal methods can be broken. All classifiers can be broken adversarially.
That's right.
But I'm starting to sort of ask myself, I mean, the way I would put it is that adversarial robustness is the worst sales pitch in the world, because the pitch is something like, your classifier is broken, but if you're just willing to sacrifice all its performance effectively, I can guarantee it won't be broken by this one little type of perturbation that no one will follow anyway. So I think that there is lots in the methodology of adversarial robustness that is hopefully useful somewhere. But I think the actual end goal of, and I should clarify that, I actually think a lot of what we do in adversarial robustness is very valuable when it comes to sort of understanding and quantifying the performance of neural networks. But I think that this sole goal of sort of adversarial performance is in some sense a little bit misplaced. And it's better to think about what are the types of changes we really see in real systems, and use this as our starting point, at least until we can fix that. Maybe once we fix that, to be clear, these things are all horribly broken. They're definitely going to be a disaster going forward. But there will be a time when the predominant threat surface of classifiers is the actual best attack point. But until we get there, I really think that it's more important to address these problems. And these problems are fundamentally empirical, and they should be treated as such.
Thank you very much. Excellent point. So we're at time. So thank you again, Zico, for a wonderful talk. And thank you to the audience for attending. Thank you very much.
All right. Thanks, everyone.